And before that, before I start, I will also write the link to my GitHub repo, so anyone can download it and go through this while when they watch later from the recording. So thanks, Dilini, for the for explaining the data wrangling part. And following from that, we can save the. So here also I'm using the Pringle Creek data. So following from the data wrangling part that Dilini described, we can come up with the clean data set that is anomaly removed, and also a flagged data set that is flagged, that actually flagged the anomalies. So I'll go from here. As I said in my previous presentation, we are considering this time frame, October the 1st to December the 31st, and this code will just do some manipulation to the data, like changing the variable names and those sort of things, and also filtering for the interested time period. And if we visualize the raw data, in the raw data, in the sense they are flagged and aggregate into 5-minute intervals. And these are the time plots that we can see for different water quality variables, colored by the by whether it is observed at the downstream or the upstream sensor. Okay, so as I discussed in my previous presentation as well, we in the framework the methods in the framework can be actually used for single sensor location as well as multiple sensor locations. So it is actually using data from the multiple sensor locations will actually improve the anomaly detection algorithm, but still this can be used for a single sensor location. So I'll first start with the single sensor location case. So we are targeting the anomalies in the turbidity downstream, and we then want to see what are the variables, what are the other water quality variables that is measured in the upstream downstream sensor to that can be used to predict the typical behavior of the downstream turbidity. So I'm just here plotting getting some plots to see the relationship, visualize the relationship. And by looking at that, we actually thought of going ahead with water level, temperature, conductance, and dissolved oxygen measured in the downstream sensor to predict the downstream turbidity. So in the modeling part, also I should mention, so during the data wrangling part, we identified some anomalies, prior identified anomalies, and for the modeling purposes, we may come up with some missing values which we don't want to impute. So if you think you need to impute the variables, then you can use any imputation methods, and this link will show you the imputation methods that I used. So basically, I have used Kalman filter-based methods for imputation. And once the data is ready, we divide the data into training and test set, and the model building is happening inside the using the training set, and the training set needs to have anomaly removed data, that is clean data, because we now try to predict the model the typical behavior of our interested variable, target variable, the turbidity downstream. So this code will show you how to get the training data. And then I fit this model, fitting a GAM model to the downstream turbidity using past values of the downstream turbidity, and then the conductance, dissolved oxygen, level, temperature from the downstream sensor location. Once we have that, we can go through some model diagnostic steps. So you can go through this due to the time constraint. I'm not going to explain that in detail, but you can see some plots and also look at the summary statistics, check whether the predictors are significant, and also how much deviance that the model is explaining. Those kind of things we check. Also some residual diagnostics. We expect the residuals to be in the model residuals to be stationary. So that part we see from here. Once the model is, once the adequate model is found, proper model is found, we can then use that model to predict the entire time series and take the residuals for the entire time series. Now we are using, so basically we use that to compute the residuals, this equation. Once we get the residuals, we then pass it to the spot algorithm. So spot algorithm is the algorithm that is used to calculate the outlier threshold for our proposed framework. So it uses the name spot stands for the streaming peak over threshold method. So that actually explain that actually uses the extreme value theory to come up with the anomaly detection threshold. It also, the code for that algorithm is in this link, and also there is this another link that you can see the algorithm clearly. Let me. Yeah, this is also in the GitHub repository. So it is well explained, and we are also writing up a paper, so you can also refer to that in later. We can share that with you. So going back to the code. Okay, so we pass that residuals through the spot algorithm to detect the outliers. So that part is done in this chunk of code. And this is just taking these two plots. So here I am plotting the turbidity downstream sensor and also the residuals from our fitted model, and see what are the true positives, true negatives, and false positives. So in this model, actually it identify all the anomalies, but it is giving considerable amount of false positives. So that we need to keep in mind. This model actually uses just data from the downstream sensor location. Okay, now come to the main part. When we have multiple sensor data, so I have Dilini and I have explained why the importance of using the multiple sensor data, and also if we are using multiple sensor data, then we have to calculate the lag time between the two sensor locations. So to calculate this lag time, we have developed these, we have write this package conduits. This can be installed by using this code, using DevTools from my GitHub repo. So this actually gives you the facility to estimate the lag time between two sensor locations by computing the conditional cross-correlation between the two sensor locations. So I will briefly go through the code, main functions of the package. So this is just getting the data. So you need to know what is the X variable, which is the variable from the upstream sensor that we use to compute the conditional cross correlation, and YT is the variable from the downstream sensor that we use to compute the conditional cross correlation. So in this example, I'm taking turbidity the upstream as the XT and turbidity downstream as the YT. And the level and temperature from upstream sensor are the conditioning variables. So we compute the lag time conditioning on the upstream level and the temperature. So this is a bit of code. First, actually, we want to get the conditionally normalized XT and YT to estimate the conditional cross correlations. So I'm not going to go in detail to that, but I'll show you how to use the function itself. So if you go to these help pages, it's clearly show you what this function does, and it describes how you can use each of the parameters. So you can basically use this the conditional CCF function. What you want to pass here is the upstream variable that you choose, that is XT, the turbidity upstream, YT, the turbidity downstream, and you need to specify what are the numerical variables. I say numerical because we might, at some point, we might have some categorical variables from the upstream, like, for example, depending on the seasons or that type of a categorical variable. If you have that, there is another parameter that you can specify. But for this example, we only dealing with numerical variables. So in this is a numeric, you need to specify what are the variables that you are using for the conditioning purposes. And then K is the how many lags, up to how many lags you want to compute the conditional cross correlation. So in this application, I'm using lags 1 to 24. And then this knots mean and knots variance are actually need to specify for each of the Z variable, we need to specify the degrees of freedom for the smoothing parameters. So that because we are using GAM models inside the code, we need to you might need to specify that, or if you not specify, it will use the default smoothing parameter that is the default value that is used in the ngCV package GAM model, GAM function. Once you specify these, you can this function will actually give you the conditional cross correlation. So once you get that, you can use these another few functions to visualize the fitted models, sort of them. And then once you get the conditional cross correlations, you can then pass it to this estimate dt function, which will actually estimate the lag time depending on the conditional cross correlations that you calculate. So basically, to recall, the lag time is the lag that gives the maximum cross correlation for a given time point. So that will actually calculate that. And this is the data you will be getting. So basically, it will give you all the data frame, the initial data frame, plus it will give you the dt, that is the lag time, and the maximum CCF, that is the maximum conditional cross correlation, and then the p-value, because we are doing some significance test to check whether the estimated conditional cross correlation is actually significant. So it will give you the p-value, or depending on that, you can see what are the significant conditional cross correlations. Once we get that, so this is some visualization of the estimated conditional cross correlations, estimated lag time, and also the p-value. And also you can use this estimate dt function, autoplot.estimate dt, to visualize the estimated lag with the predictors that we use, that is the estimated lag with the level and the temperature. Once we get that, this is just some manipulation part. And once we get the lag time, then we can, why we use this lag time, why we compute this lag time is to basically compute the lagged upstream variable. So now the upstream lag variable is not just at lag 1, lag 2, or lag 24. It's just this depends on the lag time that we estimated throughout this process. So once we know that, we can then pass it to this map lags function from the conduits package, where it will basically compute the lag variables from the upstream sensor. So you just have to pass the data and then specify what are the upstream data, that upstream variables that are in the past data frame, and also what is the downstream variable in the data frame in downstream column. Basically, you need to specify the column name for upstream and downstream variables, and also you need to give the column for the lag that is the column. Once you get that, you will the function, the upstream, sorry, the map lag function will basically output the data frame with the lagged upstream variables, replaced with the upstream original variable. After that, it's all about then modeling. So we did some visualization as before. So now we are visualizing the turbidity down with the upstream lagged variables. Once we get that done, we are going to the modeling part. So basically, we now model the turbidity downstream with turbidity with past turbidity downstream. Like we all in this model also we are using some autoregressive terms to capture the autocorrelation. I'm autoregressive. By autoregressive, I mean the past values of the response variable. And also we pass the level upstream, lagged level, and the temperature upstream dt, that is the lagged temperature upstream, and the lagged temperature conductance. Once we build that model, we then do some model diagnostics and check the residuals. Residuals are good, stationary, and does not have any pattern. Again, I should note that the modeling is done in the training set where we don't have any anomalies in it. After getting the model fixed, then we use that model to predict the entire turbidity series for the entire turbidity series. And then from there, we can compute the residuals. So residuals is just the difference between the observed value and the prediction from the model for the entire period. Once we get that, we then pass it to the spot algorithm to identify the anomalies. So this is the plot. So you can see that there's one false negative, which is actually missed from this model. But I should mention, since it is not showing you in the residual plot, that is because when we are calculating that upstream lagged variable, we are getting some missing values because the way we are calculating the lag. And that missing value corresponds to this missing residual, and that's why we actually couldn't identify this true outlier in the data. However, this model is actually giving less false positives than the model that I have shown you previously. Yeah, so that comes to the end of the code sharing session for me. Happy to take any questions afterwards. And I have shared the link to the repo, and also you can see the package in my GitHub. Yeah, thank you.